friends. In previous classes, you have studied the 6 degree of freedom equations of motion. Today, we will try to find the trajectory of the aircraft with the help of these equations. Before we proceed to find the trajectory, we must have to be familiar with the all forces and moments acting on the aircraft. However, you already know, but before proceeding, let us take a quick review of these forces and moments. You know all the dimensions and all the inertial criteria of all the inertial properties of the aircraft, and you know all the aerodynamic coefficients. Using these coefficients and the inertial property, you can find all the forces and moments. You know all the dimensions of the aircraft. You know dimensions means you know the C bar, you know the wingspan, you know the area of the aircraft, and you are familiar with the inertial properties means you know the mass, inertial components, that is Ixx, Iyy, Izz, and the cross products Ixy, Iyz and Ixz. And you already know all the aerodynamic characteristics of the aircraft, means you know all the aerodynamic coefficients, so CL naught, CL alpha dot, CLQ, CL delta E, CL delta F. If you have all these aerodynamic coefficients, you can find the lift acting upon the aircraft, because using these coefficients you can find the CL, and CL is given by CL naught plus CL alpha into alpha, CL alpha dot into alpha dot C bar by 2b, so CLQ into QC by 2b plus CL delta E into delta E plus CL delta F into delta F. So, you can using these coefficients you can find CL, and once you have the CL, you can find the lift acting on the aircraft by half rho b square S CL. Similarly, you have all the drag coefficients, you know the CD naught, CD alpha, CD alpha dot, CDQ, CD delta F, CD delta A, CD delta R, and all other remaining coefficients, and from there you can find the CD, and once you know the CD you can find the drag, and you can find the Y forces also acting on the aircraft. Once you have all the forces, you can decompose them into body frame X, Y and Z axes. How you do this? You have the angle of attack and side slip angle. If the velocity component of the aircraft in the body frame are the U, V and W, the angle of attack alpha will be tan inverse W by U, and beta will be tan inverse V by U. So, now if you have the alpha and beta and all the forces, lift force, drag force and Y force, then using these two angles you can find the F aerodynamic x, F aerodynamic y and F aerodynamic z acting in the body axis of the aircraft. Similarly, if you have all the moment coefficients CL naught, CL beta, CL beta dot, CL p, CL r, CL delta A, CL delta r, you can find the CL. And once you have the CL, you can find the rolling moment L is given by half rho v square s CL into C bar. Similarly, you can find the pitching moment and yawing moment also. Now, you have all the aerodynamic forces and moments acting on the aircraft. Now, the task is to find all other forces and moments acting on the aircraft. What are the other forces? The thrust force and the force due to gravity. In case of propeller aircraft, the force basically depends upon the throttle and the velocity of the aircraft, and if you can model it, you can find it. There are a lot of methods given in the books, or you can prepare a lookup table for the different velocities and different throttle levels, and then you can pick a value of the thrust from there for your particular aircraft, for your particular throttle level and velocity. And the third force is the gravity force. If you know the orientation of the aircraft, the psi, theta and phi, you can find all three gravity forces. We will see it later. So, finally, you have all the three aerodynamic forces, F aerodynamic x, F aerodynamic y and F aerodynamic z, and the thrust forces you can decompose it in the x, y and z direction. You know the orientation and mass. So, using the gx, gy and gz, the gravity components in x, y and z direction, you can calculate the gravitational force acting on the aircraft in all three axes. Now, you will be using these forces and the equations of motions that we have derived in the previous classes, and we will see how we can find the trajectory of the aircraft. In previous classes, we have derived 6 degree of freedom equations of motion, and we have two set of equations, each set 3 equations. The first is the conservation of linear momentum equation, and the second set conservation of angular momentum equations, and they were, if you talk about the conservation of linear momentum equations, we can write m u dot plus q w minus r v m g x, the gravitational force, F aerodynamics in x direction and thrust force in x direction. The second equation, m v dot plus u r minus p w the gravity force in y direction plus aerodynamic force in y direction n plus thrust force in y direction. And the third equation mw dot thrust force in z direction. And the second set of equation, the conservation of angular momentum equations, and these were p dot I x x minus r dot I x z minus p q I x z plus r q I z z minus I y y. The rolling moment due to the aerodynamic force and rolling moment due to the thrust L A plus L T. The second equation q dot I y y plus p r I x x minus I z z plus p square minus r square I x z is equal to aerodynamic plus and thrust. And the third, the yawing moment due to the aerodynamic forces and thrust. So, we had derived this sixth set of equations. We have the information of aerodynamic forces, all three aerodynamic forces. We know the thrust forces, and we know all the gravity components, and we have the initial condition of the aircraft. Then using this set of equations we can find the three velocity components u, v, n. The solution of these equations will give us the three velocity components u, v, and w. You can solve this set of equations using any numerical method. There are a lot of tools. You can find some solver in the MATLAB also, or I personally like to solve these kind of equations with the help of Runge-Kutta methods, because these equations are coupled. If you see, the u dot is here and u is utilized here, similarly with the w and v also, and this set of equations also. So, you can solve using any numerical method, and finally, you will get the u, v, w, and from here solving this set of equations you will get the p, q, and r. Now, the question is how we can find the trajectory of the aircraft. We have three velocity components, and these velocity components are in body frame of the aircraft. And if we want to determine the trajectory of the aircraft, we will require these velocity components in the inertial frame, because whenever we talk about the trajectory, obviously we are talking in terms of the inertial frame. So, we need any methodology to convert these velocity components, these body axis velocity components, into the inertial frame. And if you remember, we had studied the Euler angles, Euler rotation. With the set of those equations, we can convert. Let us see a quick review of the Hilar angles. Suppose this is our inertial frame. These are 3 axes x, y and z, and we have to, this is in the inertial frame. If I write it x1, y1 and z1, and we have another frame. This is our aircraft body frame. So, how we can transform our equation from this frame to this frame or this frame to this frame? We can reach from one frame to another frame with the help of 3 rotations, and there are many type of rotations used, but in the Hilar we use this sequence of the rotation 3, 2, 1. First we rotate our frame about the z axis, then the new y axis which we got after the rotation in the z axis, and lastly we rotate our frame about the new x axis which got after the second rotation. Let us see it. Suppose I have top view of my aircraft. This is the positive y, this is the x, and if you rotate it like this is the psi, this is called the psi rotation. Initially we were in the inertial frame, and suppose this was our x1 and this is the y1, we are representing inertial frame with the x1 and y1, and finally we are trying to come into the body frame, and that will be our x, y and z. In intermediate we have got this frame called x2 and y2, and for this rotation the z will remain common, z1 is equivalent to z2, because we are rotating about this z axis only. We can write in matrix form this rotation. Suppose our velocity components in inertial frame are u1, v1 and w1, and after the psi rotation it becomes u2, v2 and w2. This u2, v2, w2 is an intermediate frame, and this we got after the rotation psi. We can write this matrix cos psi minus sin psi 0 sin psi cos psi 0 0 0 1, and the second rotation we rotate about the new y axis, and using that rotation you can get u2, v2, w2 u3, v3 and w3. This is in the second intermediate frame, and for this we get the matrix This we get due to the theta rotation, cos theta 0 sin theta 0 1 0 and minus sin theta 0 and cos theta. And finally, the third rotation. In this rotation we had Z1 and Z2 same. In this rotation we have Y2 and Y3 same, because we are rotating about this Y2, and this after the rotation also it will remain same. In third rotation we can get U3, V3 and W3 and finally we reach in body frame, and this is U, V and W. So, after these 3 rotations finally we have reached from this inertial frame to the body frame, and in this case x3 is nothing but the x, because we are rotating about this x3. If you see this rotation, suppose this was my aircraft, this is x and this is z. Actually this is x2 and this is z2. This after the theta rotation we will get x3 and z3. The y2 and y3 will remain same. In this third rotation you will get the matrix 1 0 0 0 cos phi minus sin phi 0 sin phi and cos phi. In third rotation we have front view of the aircraft. If this is my front view, then suppose this is our y3 and this is z3. For this rotation, for the positive phi, the right wing down is the positive phi. So, right wing down means if this is my front view, it will be like, it will become like this, and this is my final y and this is z, and this angle is phi. So, using these 3 rotations we can convert our frame from inertial frame to the body frame or body frame to inertial frame. If we can combine all these rotations in one equation, we will get an inertial frame, all 3 velocity components, and this can be given by the multiplication of 3 matrices. This UVW is in body frame, and by multiplying this matrix we are able to get U1, V1, W1. This is in our inertial frame, and this is our desire because we want to find the trajectory. You can write U1, V1, W1 x1 dot, y1 dot and z1 dot. So, from here we can find the x1, y1 and z1, and this will ultimately give us the trajectory of the aircraft in the inertial frame. From these three set of equations, we already have got the UVW, this UVW, but to find the U1, V1, W1, we require psi, theta and phi also, and from where we will find this. So, to get this, we will do a small manipulation. The matrix that we had derived to convert the body frame into inertial frame or inertial frame to the body frame, this we call the flight path equations. So, now our target is to find the three other angles psi, theta and phi. And what information we already have? We know the PQR. So, we have to find the psi, theta, phi from the PQR, because this is the rotation, and if you have the rotation and if you know the initial condition of rotation, obviously we can find the orientation, and that we will try to find here. If we have the angular velocity of the aircraft, you can write it this PQR and are the rotations, the angular speeds in the body frame of the aircraft. So, we can write Pi plus Qj plus Rk, and if you know the rate of Euler rotations, we can write it the angular speed of the aircraft, the psi dot plus theta dot plus phi dot. Somehow, if I am able to determine the expression for this in terms of I, j and k, and if I compare with this equation, I will get the psi dot, theta dot and phi dot in terms of p, q and r. How we can do this? The three rotations that we performed to determine the Euler angle psi, theta and phi. The first was the psi, and this was about the z axis, and for this, suppose we transformed our coordinate system from body axis, and in the body axis we had the unit vectors I1, J1 and K1, and from here we got the I2, J2 and K2, and the rotation that we performed was the psi. Here the K1 will be equal to the K2 because we are doing this rotation about the z axis. So, K1 is equal to K2, and I can write the psi dot vector is equal to psi dot K1, and this is equal to psi dot K2. Similarly, when we did the second rotation, that was from I2, J2 and K2 to I3, J3 and K3. For this, we got from this rotation we got the theta angle, and this we are doing about the y axis, means this J2 and the J3 are the same, and we can write the theta dot vector is equal to theta dot J2 or theta dot J3. In the third rotation, that was the phi that we performed about the x axis, that was the x 3 or I 3, and we got we reached from I 3 j 3 and k 3, the rotation was phi, and we reached into this body frame, that was the I, j and k. This rotation we are performing about this x 3 axis or I 3. So, I 3 will be I, and we can write this phi dot vector is equal to phi dot I 3, and this is equal to phi dot I, and we can write the omega using these equations. Omega is equal to psi dot k 2 plus theta dot j 3 plus phi dot I. Why I am using this and this only? Because our ultimate aim is to reach in I, j and k frame in this body frame, and if I start from here, if I take this psi k 1, then I will have to transform my frame 3 times. The first from k 1 to k 2, and then k 2 to k 3, and then k 3 to k, and this will take the 3 rotations. If I start from k 2 direct, then I can reach into the I j k frame only after the 2 rotations. Similarly, if I start from theta dot j 3, I will require only 1 rotation, and I will reach into the I j k frame. If I start from here, I will require 2 rotations. That is why I am picking this one, and this is already in I form, no requirement of any rotation. Now, how we can find this k 2 in terms of I 3 j 3 and k 3. If you remember our second rotation, that was the theta, and we were getting the I 2 j 2 and k 2, and the rotation matrix was, suppose this is I 3 j 3 n, this was the second rotation, that is the theta, and this was given by cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. So, from here I can get k 2 in terms of I 3 j 3 and k 3, and I can write k 3 is equal to, sorry, k 2 is equal to this k 2 minus sin theta I 3 plus cos theta k 3. And I have to find this I 3 is already, I know is I, so I can eliminate it and I can write it I. Now, I am left with k 3, and for this I can use the third rotation, and that was I3, J3 and K3, and the matrix we had 1 0 0, and here we had I, J and K. The matrix was 0 cos phi minus sin phi, 0 sin phi and cos phi, and from here I can get K3 in terms of I j k, and K3 is sin phi j plus cos phi k. And if I substitute it here, I will get K2, this is unit vector, sin minus sin theta I plus cos theta, and K3 is sin phi j plus cos phi k. So, now I have K2 in terms of I j and k. So, this task is complete, and I have to find J3 also in the terms of I j and k, and from here I can write J3 is equal to cos phi j minus sin phi k, cos phi j minus sin phi k. Now, we do not require these equations. So, finally, I have omega psi dot, and K2 is what? Minus sin theta I plus cos theta sin phi j plus cos theta cos phi k plus theta dot J3, and this I can write cos phi j minus sin phi k. And this is already we have plus phi dot I. And now, if I rearrange these terms and if I compare with this first equation, I will get P is equal to phi dot minus sin theta psi dot, Q is equal to cos phi theta dot plus cos theta sin phi psi dot, and R is equal to cos theta cos phi psi dot minus sin phi theta dot. And if I write it in a matrix form, I can write the P, Q, R is equal to one 0 minus sin theta 0 cos phi cos theta sin phi and 0 minus sin phi cos theta cos phi. And this in multiplication with phi dot theta dot and psi dot. And this set of equation we call the kinematic equation. Once we have this psi, theta and phi, we know the orientation of the aircraft. If you remember, we had derived the gravity equations using this psi, theta and phi, and those equations were given by, let me rewrite here, g x is equal to minus g sin theta, g y is equal to g cos theta sin phi, and g z is equal to g cos theta cos phi. Now, we have the gravity components. You can solve this set of equations in iterations using some numerical method, and if you are solving it for a small time delta t, whatever you get after this, suppose it is 0.001 second or 0.01 second, is usually we keep it very small. Once you solve it for a delta t time, you will get the new values of these forces, this u v w and p q r means this forces, and this of course you will get L, M and also these new moment values. And if you keep iterating for the next iteration, whatever you have got the new values, that will work as the initial condition, and you will get the values after 2 delta t, and similarly if you keep iterating, you will get a continuous path of the aircraft, that is our trajectory. We have developed a graphical user interface for the 6 degree of freedom simulation. In this, here you can feed all the aerodynamic coefficients associated with the longitudinal motion, the lift coefficients, drag coefficients and the pitching moment coefficients. In this window, all the aerodynamic coefficients associated with the lateral and directional motion of the aircraft, coefficient for the y force, all the rolling coefficients and yawing coefficients. Here parameters associated with the dimensions of the aircraft and all the inertial properties, all the initial state of the aircraft. And in this window, if there is any wind, you can put here. Altitude is divided in different slots. In each slot, whatever the component of the velocity is can be given here. It's in inertial frame. The number of elements in all the boxes will be same. The start time of the wind, the stop time of the wind. This window has nothing to do with the simulation, but you can get a rough approximation for the trim. Suppose I want to fly at 100 meter altitude with 15 meter per second. For this, my elevator input is this much and the throttle is required is this. This is the input window. I can give the inputs for the different control surfaces. Suppose I want to trim at 100 meter altitude with 15 meter per second. For this my elevator input is this much. So if I give, if I want to give more inputs, I can add here. Like if I give elevator input starting from 50 for 10 seconds and suppose 5 degrees. So similarly I can add as many inputs I want to give, and similarly for the aileron, rudder and flaps also. This is my throttle. And this is the simulation parameter. For the duration I want to simulate, and the step size for the internal calculations. And here is the engine parameters. I can select the type of engine. I execute it. Aerodynamic coefficients that we entered here, you can find them analytically. For this you can refer the book Aircraft Dynamics by Marcelo R. Napolitano or Aircraft Design by Daniel Remer. You have any other book, you can follow that. You can calculate them with CFD simulation also. If you want to get more accurate values, you can perform a wind tunnel test, then you can calculate all these aerodynamic coefficients. Now if I want to see the angle of attack, it will be plotted here. Pitching angle, you want to see this path in 3D space, the velocity, and whatever I will select here, they will appear. The first 4 will appear here. Suppose I want a tailwind of 2 meters per second. I am flying at approximately 100 meter altitude. So if I add till 100 meters, a wind of I have added from 10 to 1 kilometer altitude, 2 meter per second wind, and I am sure that my aircraft is not going beyond those altitudes. Starting from 20 seconds till 45 seconds, and now if I execute it, here you can see when there is wind, the angle of attack gets changed. Again when wind is not, then again there is a change, there is a transition actually. The altitude it's losing, then again it's gaining when the wind is not there. Because this is tailwind, that's why it's losing its altitude. Here are some tools, you can use them. Suppose I want to see this area much closer, I can zoom it. We have put this software on the Flight Laboratory IT Kanpur website. It's open source, you can download. If you have any idea, you can add into this. If you have any doubt, you can ask me. My mail ID is vijayD@iitk.ac.in. You can ask the questions on the forum also. We will be happy to answer. Thank you very much.